Think about the ocean for a second. It's just this vast blue heart of our planet, isn't it? Pumping life and, well, regulating pretty much everything from the food we eat to the air we breathe.
Exactly. It's not just pretty scenery. It's fundamental. The engine of Earth's systems.
Right. And today we're plunging into some really significant shifts happening just beneath the surface. Big changes.
That's right. We're going to be looking at the latest findings from the IPCC report, focusing on how climate change and ocean acidification are really impacting our global oceans.
And we're focusing on specific areas, too.
Yep, 7 distinct ocean regions, crucial ones, everything from the icy polar waters right down to the warm embrace of coral reefs.
7 regions sounds like quite a journey. And what we want to do in this deep dive, it needs to be crystal clear. We need to understand exactly what these changes are, how scientists track them, and really crucially, why this should matter to you no matter where you happen to live.
Precisely. The goal is to cut through the complexity, pull out the most important insights, and, connect the dots so you can really see the unfolding story of our changing oceans and what it means.
Okay, let's dive right in then. The big picture first, the changes across the ocean as a whole. What are the key sort of overarching findings?
Well, the report states with high confidence, that's important, that most of the ocean is getting warmer and more acidic.
Okay, warmer and more acidic. Is that everywhere at the same rate?
No, there are regional variations in the speed, but what's really striking is that until about 2040, the projections show very little difference in these trends. And that's regardless of the different greenhouse gas emissions scenarios we might follow.
Hold on. So whether we drastically cut emissions right now or not, the next, 15, 20 years of ocean warming and acidification are kind of locked in?
Largely, yes. It's a sobering thought, isn't it?
It really is. What else is happening on a global scale?
We're also seeing a significant acceleration in sea level rise. I mean, the rate we've seen since the mid-19th century, it's higher than anything in the last 2,000 years. High confidence on that, too.
Wow. 2 millennia. Can you put some numbers on that?
Sure. So the global average sea level rose by about 19 centimeters between 1901 and 2010.
19 centimeters.
And the rate of that rise actually increased. It was about 1.7 millimeters per year in the earlier part of that period, but jumped to 2.0 millimeters per year between 1993 and 2010.
19 centimeters might not sound like a huge amount to some people, but when you think about the knock-on effects, like increased coastal erosion, bigger impacts from storm surges.
Exactly. Those centimeters really, really add up for coastal communities and makes a massive difference.
Definitely. Okay, what about the physical forces? Winds, waves, the ocean's so dynamic.
Yeah. Changes in wind patterns are proving a bit trickier to pin down. There's currently low confidence in directly linking potential increases in wind speeds in certain areas, these places called Eastern Boundary Upwelling Ecosystems, or EBUEs.
Right, those really productive coastal zones driven by wind.
That's them. So low confidence in linking stronger winds there, specifically to climate change. Now, these wind changes could affect how deep the surface layer mixes and the intensity of upwelling.
Which brings nutrients up.
Exactly, nutrient-rich water to the surface. But there isn't strong agreement yet on whether upwelling will generally get more intense or less. It's complex.
Okay, and waves.
When we look at surface waves, there's medium confidence that wave height has increased in the North Atlantic, north of 45 degrees latitude, since the mid-1950s.
So bigger waves in the North Atlantic.
Yes. But again, predicting future changes for wave heights across most of the ocean, that's still really challenging. Low confidence in future projections there.
Okay, understood. Let's tackle ocean acidification then. We hear that term a lot. What's the latest?
This is a really critical one. The report shows, again, high confidence that marine organisms are very sensitive to the levels of acidity projected under more atmospheric CO2.
Makes sense.
And particularly ecosystems that rely on calcium carbonate. Think coral reefs, certain types of plankton.
Things that build shells or skeletons.
Precisely. Acidification basically reduces the availability of the carbonate ions they need for that building process. But what's truly remarkable and frankly concerning is the speed of this change.
How fast are we talking?
The rate of acidification is estimated to be 10 to 100 times faster than what the planet saw during the natural transitions between ice ages.
10 to 100 times faster.
Yes. Think about that geologically. In the blink of an eye, we are fundamentally altering ocean chemistry at a rate that's just unprecedented in the last 65 million years. maybe even longer.
Wow, 65 million years, that just doesn't leave much time for marine life to adapt, does it? It's like
Yeah.
throwing them a curveball they've literally never seen before.
That's a good way to put it, exactly. And related to all this, we're also seeing shifts in ocean oxygen levels.
Less oxygen.
In some key areas, yes. There's medium confidence, but it's considered very likely due to external factors like warming that oxygen has decreased in the upper layers since the 1960s, particularly in the equatorial Pacific and Atlantic.
Okay. But not everywhere.
Interestingly, no. Oxygen has actually increased in other areas, parts of the North and South Pacific, the North Atlantic, the Indian Ocean. It's variable.
Why the decrease in those specific zones, then?
It seems to be largely due to two things: increased microbial activity deeper down, using up oxygen, and also reduced supply of oxygen from the surface because the ocean is becoming more stratified.
Stratified, you mean layered?
Yeah, essentially the ocean is layering itself more distinctly based on temperature and salinity. Warmer water is less dense and sits on top, and this layering effect can prevent the normal mixing that brings oxygen-rich surface water down.
Okay. So warmer water holds less oxygen anyway, like a warm soda goes flat faster, right?
Right.
And then these layers aren't mixing as much, so the deeper waters are getting starved of oxygen. That sounds like it could have huge consequences.
It absolutely could. And stratification is linked to that point about thermal inertia. The ocean warming slower than land.
Right. Explain that connection again.
With this slower warming, the thermal inertia means the ocean takes longer to heat up overall compared to the air or the land. But, and this is crucial, even small temperature increases, just 1 to 2 degrees Celsius at the surface, can be enough to trigger mass coral bleaching events. High confidence in that link.
Just 1 or 2 degrees. Wow.
And these zones of similar temperature isotherms, we call them, they're moving quite rapidly towards the poles or deeper. This essentially forces species to migrate to find water that's the right temperature for them.
Imagine trying to pack up your entire habitat and move because the temperature's suddenly wrong.
That's the challenge many marine species are facing right now.
Okay, so globally, warmer, more acidic, losing oxygen in key areas, sea levels rising faster. Quite a picture. Let's zoom in now on those 7 subregions you mentioned. First up, high-latitude spring bloom systems. What's happening way up north and south?
Right, in these colder systems, often near ice, we have high confidence that warming is affecting the timing, the phenology, and also the abundance and distribution of plankton.
The base of the food web.
Exactly. And the changes are significant. For example, in the northeast Atlantic, some types of warm water zooplankton have shifted northward by up to 1,000 kilometers since 1958.
1,000 kilometers?
Yeah. They're essentially replacing the cold water species that used to be there.
Yeah.
And this fundamental reorganization at the bottom of the food chain, it's leading to changes in fish populations higher up, too.
That's a massive displacement. So what does this mean for things we care about directly, like fisheries?
Well, there's a real potential for a significant reorganization of commercial fish stocks. That could cause serious social and economic disruption for communities that rely on those fisheries.
So fishing grounds could literally move.
They are moving. And while some earlier studies suggested maybe increased productivity in some northern fisheries due to warming, more recent research shows it's really complex. Ecosystems are responding in unpredictable ways, making long-term forecasts pretty difficult.
Right. It's not just a simple case of warmer equals more fish everywhere. Okay, let's shift gears. Equatorial upwelling systems, those really biologically rich areas near the equator where deep water comes up.
These systems, both in the Pacific and Atlantic, have seen significant temperature increases. Surface warming.
Okay.
Interestingly, sea level has actually been decreasing slightly in the eastern equatorial Pacific since 1993. But a big unknown here is El Niño.
The El Niño Southern Oscillation, ENSO, that big climate pattern.
Exactly. It has a massive influence on these regions, bringing warm and cool phases. But there's currently low confidence in how climate change itself will impact the ENSO cycles in the future.
So if we don't know how ENSO will behave, it's hard to predict exactly what will happen in those upwelling zones long term.
Precisely. There's also research suggesting that the big subtropical gyres, those large circulating ocean currents, might be expanding.
And squeezing the upwelling zones.
Potentially, yes, at the expense of these equatorial upwelling systems. If that happens in the North Pacific, for example, some models suggest it could shrink the upwelling area, possibly leading to a big drop in primary production and maybe fish catches by the end of the century.
So overall, fisheries in these crucial equatorial regions face increased vulnerability.
That's the assessment, yes, though the confidence in that specific projection is still low. Lots of uncertainty there.
Okay. From the open ocean to semi-enclosed seas, places like the Mediterranean, what unique changes are happening in these more contained waters?
Well, the Mediterranean Sea is definitely warming, and it's becoming more saline, saltier. We're also seeing the thermal stratification, the layering lasting for longer periods each year.
Okay.
And what's particularly interesting is that there seem to be some abrupt shifts back in the late 1980s, not just in the Med, but also the North Sea, Baltic, Black Sea.
What kind of shifts?
Changes that coincided with shifts in zooplankton populations, anchovy numbers crashing in some areas, and even more frequent algal blooms and these sort of mucilage outbreaks, slimy stuff, linked to the warmer, more layered waters.
A whole ecosystem shift in a pretty short time, then. And what about longer trends in the Med?
We're definitely seeing a northward spread of warm water species. It's often called tropicalization. High confidence in that. Species are moving up from the south through Gibraltar, through the Suez Canal, into previously cooler northern areas.
Like ecological invaders, almost.
In a sense, yes. And sea level is rising too, particularly noted in the northwest Mediterranean. It seems these semi-enclosed seas can be quite sensitive indicators of warming trends.
Like little bellwethers for the bigger ocean. Okay, let's move on to coastal boundary systems, those really productive regions where land meets sea. What's the general picture there?
These regions are vital. Think of the Bohai and Yellow Sea, Southeast Asian seas, the Canary Current off Africa, the Benguela Current. Generally, they are warming, but the rate isn't the same everywhere.
Any exceptions?
Yeah, for example, the Gulf of Mexico and the Caribbean didn't show a significant warming trend during the specific period the report looked at closely, 1950-2009. And rates of sea level rise and acidification also vary a lot within these coastal systems. They're complex interfaces.
Let's zoom in on a couple. What about the Bohai Yellow Sea and East China Sea? They're already under huge pressure from human activity, right?
They really are. And these areas have seen rapid sea surface temperature increases since the early 1980s. It seems linked to things like a weakening East Asian monsoon and warmer currents, like the Kuroshio, pushing in.
Then what else?
At the same time, dissolved oxygen levels have dropped, and the extent of hypoxic low oxygen areas near the coast has expanded. So it's this worrying combination, warmer water and less breathable conditions for marine life.
That sounds really bad. A double whammy. What about the Southeast Asian seas, including the Coral Triangle? That's a global hotspot for marine biodiversity.
Absolutely critical region. It's also seen significant warming and rising sea levels. And crucially, since the early 1980s, there have been numerous mass coral bleaching events.
Bleaching, we hear so much about that.
And the report has high confidence that these events are very likely due to human-caused climate change. Local stresses matter too, of course, pollution and overfishing, but the projected increases in sea surface temperature are the major ongoing threat to these incredibly valuable ecosystems.
The decline of coral reefs there must be a huge concern.
It's a major, major concern. Devastating losses in some areas.
Just heartbreaking. Okay, what about those eastern boundary upwelling ecosystems, the EBUEs, like the Canary and Benguela currents off Africa? We touched on wind uncertainty earlier, but what else?
Right. In the Canary Current, there's evidence of warming since the early 80s. But, as we said, low confidence still about whether the upwelling itself is getting weaker. However, there is medium evidence and agreement that primary production, the base of the food web, has decreased there over the last couple of decades.
So, less life being produced overall.
Seems that way. And we're seeing changes in where certain fisheries species are found. They're moving. The Benguela Current, further south, also shows a warming trend and documented shifts in the phytoplankton communities. These changes worry ecologists studying the rich biodiversity hotspots in these regions.
And the California Current, another EBU.
Yes, off the U.S. West Coast, also known for high productivity. Interestingly, fish catches there have been relatively stable since 1950, despite fluctuations. It's a vital habitat for seabirds and marine mammals, too. So again, regional differences.
Okay, so each of these diverse coastal systems is reacting in its own complex way. Let's head further offshore now to the subtropical gyres, those huge swirling regions in the middle of the oceans.
Right, the big gyres. They've generally seen increased temperatures, too. Interestingly, salinity has actually decreased in the North and South Pacific gyres. Less salty.
Why would that be?
Likely changes in rainfall patterns and evaporation linked to large-scale climate phenomena. These regions are heavily influenced by things like the Intertropical Convergence Zone, the South Pacific Convergence Zone, and those big climate drivers we mentioned, ENSO, and the Pacific Decadal Oscillation, PDO.
And how are those big patterns expected to change?
That's still a bit of a question mark. There's low confidence in how these major climate patterns themselves will change with further warming, which makes predicting the gyre's future tricky.
So uncertainty remains about the forces shaping these vast areas, but what are we seeing clearly?
Well, we have very high confidence about an increased frequency of mass coral bleaching and mortality on reefs within these gyre regions since the 1980s, leading to significant losses of coral cover there, too.
Even far from direct coastal impacts sometimes.
Exactly. Sea level rise is also impacting crucial coastal ecosystems on islands within these gyres, seagrass beds, mangrove forests. Tuna fisheries, particularly in the Indian Ocean, have shown vulnerability to sea temperature changes. And there's potential for stronger tropical cyclones, more intense rainfall, though likely with regional variations.
So even the seemingly stable open ocean is far from untouched, particularly coral reefs and fisheries. Okay, finally, let's venture into the real depths. The deep sea, below 1,000 meters. What's happening down there?
The deep sea is also warming, although the rate is generally slower than at the surface.
Okay.
Warming's been observed over multiple decades. It's often minimal at mid-depths, but seems to be increasing closer to the seafloor in some areas, like parts of the Southern Ocean. And you have to remember, deep waters have very long residence times.
Meaning the water down there has been away from the surface for
centuries, even millennia in parts of the deep Pacific. So the warming we see now is from surface changes long ago. And because deep-sea species often have very specific, very narrow tolerances for temperature and oxygen.
They're quite specialized.
Extremely. So we're likely to see shifts in their distribution, maybe even regional extinctions, as conditions change. It's a kind of hidden impact unfolding in a part of the ocean we rarely think about.
A silent, slow-motion crisis in the abyss. Okay, we've covered so many different changes across these regions. How confident are scientists in actually attributing these changes to us, to human-caused climate change and ocean acidification?
Right. For the big global trends, the overall ocean warming, the acidification, and those widespread mass coral bleaching and mortality events, there's very high confidence in detecting the change and high confidence in attributing it directly to atmospheric greenhouse gases from human activities. The fingerprint is clear.
Okay, so the big stuff is clearly linked. What about the others?
For some other changes, like shifts in wind-driven upwelling or pinning down the exact reasons for declining calcification rates in some organisms, the confidence is lower.
Why is that?
Often it's because it's just harder to detect a clear long-term trend amidst natural variability. Or sometimes the climate models don't perfectly agree on these more complex regional processes. Detection or attribution is just trickier.
Okay, so the human fingerprint is clearest on the major global shifts and the most dramatic impacts like coral bleaching. So let's pivot to the consequences. What does all this mean in the real world? How are these shifts impacting ecosystems and, well, us? Human activities depending on the ocean.
The report really highlights rapid shifts in fundamental ecosystem services. The benefits we get from the ocean. Clean water, food, climate regulation.
And we need to adapt.
Absolutely. Adaptation and mitigation strategies are crucial. One promising area is blue carbon.
Right. Carbon stored in coastal ecosystems.
Exactly. Mangroves, seagrasses, salt marshes, they capture and store a lot of carbon. This offers potential for both adaptation protecting coasts and mitigation storing carbon. But we still need to figure out the best ways to implement these approaches effectively.
And protecting them stops them releasing carbon too, right?
That's a key point. When these coastal habitats are degraded or destroyed, they can release huge amounts of stored CO2. So protecting them is definitely a double win.
Makes sense. What about fisheries and aquaculture? Huge global food source, millions of livelihoods.
Yeah, fisheries face really significant challenges. Habitat loss, like coral reefs degrading, species literally moving to new areas, sometimes across borders, increased rates of disease, invasive species spreading, and those fundamental changes in primary production we talked about.
It sounds like a perfect storm of problems.
That's a lot of pressure. There's medium evidence and agreement that we might see increased fish production in some high-latitude regions as waters warm and new areas open up.
Okay, some potential winners.
Potentially,
Yeah.
But likely significant decreases in lower-latitude tropical areas. Aquaculture fish farming is also vulnerable, especially to extreme weather events and sea level rise impacting coastal farms.
So what can be done? What are the adaptation options?
Things like developing early warning systems for harmful events like algal blooms, diversifying the species being farmed or caught, adopting much more flexible, adaptable management practices, conducting thorough vulnerability assessments to know where the risks are greatest.
And specific examples?
Well, things like tuna fisheries in the Pacific. They clearly need international cooperation because the fish don't respect national boundaries and they are moving. Or for coral reef fisheries, efforts focus on reducing local pollution, promoting less damaging fishing methods, maybe creating alternative livelihoods.
So flexibility, cooperation, looking at the bigger picture, that seems key. What about other sectors? Tourism, for example, so often linked to healthy coasts.
Tourism is definitely highly susceptible. Extreme weather events, obviously, but also just the physical impacts of sea level rise, coastal erosion eating away beaches, damage to ports, resorts, infrastructure.
And the main attraction disappearing.
Right. Coral reef bleaching directly diminishes the appeal of countless destinations. A bleached, dying reef just isn't the tropical paradise people travel to see.
No, definitely not. Okay, what about big industries? Shipping, oil and gas.
For shipping, there might be some potential benefits, strangely enough. The reduction in Arctic sea ice could open up shorter transit routes between, say, Asia and Europe.
The Northwest Passage, the Northern Sea Route.
Exactly. But that immediately brings huge challenges. It needs robust transit management systems, new safety protocols, international legal frameworks for these newly accessible and ecologically sensitive areas.
Right, it's not straightforward. And oil and gas.
Well, there's a continuing trend towards more seafloor, completions anyway, and the warming in the Arctic is certainly making that region more accessible for further resource extraction. Although the long-term influence of warming on, seafloor stability around pipelines and rigs, that's still being debated.
Okay. And what about the most direct impacts on us, on human health?
Several potential threats there. Diminished security of water and food supplies in some coastal regions, increased risks from extreme weather, coastal flooding, changes in the distribution of diseases.
Like what?
Things like waterborne illnesses, cholera may be spreading, increases in harmful algal blooms which can contaminate seafood or make swimming unsafe. We might also see more marine toxin issues, like ciguatera fish poisoning, which seems linked to warmer waters and degraded reefs.
So these ocean changes have these far-reaching ripple effects, touching almost every aspect of our lives, directly or indirectly. One last area, maritime security.
Yeah, the emergence of those new ice-free seaways in the Arctic, while maybe offering economic advantages, it could also become a source of increased international tensions, questions about sovereignty, access rights, resource claims. It requires new governance structures.
And the navies themselves?
Well, naval operations contribute to greenhouse gas emissions too, of course. There are ongoing efforts within many military organizations to try and reduce their environmental footprint, use alternative fuels, etc.
It really sounds like we need more international cooperation than ever to navigate all this. The report mentions global frameworks for decision-making.
Yes, absolutely essential, especially because most of the ocean, the vast majority, lies beyond any single nation's control outside exclusive economic zones. So we need strong, general frameworks, international conventions to manage these shared resources and stressors.
Are there examples of things working?
Well, initiatives like the Coral Triangle Initiative that brings together several Southeast Asian nations to cooperate on managing that vital region provide important models for regional action. But we also face really complex legal questions now, like how does sea level rise affect existing maritime boundaries? If an island nation shrinks or disappears, what happens to its maritime zone?
Wow. The map itself is literally changing.
It really underscores the interconnectedness of the whole global system.
Definitely. Okay, so finally, looking ahead, what are the really big unanswered questions, the emerging issues scientists are focused on now?
Oh, there are many. A key one is understanding the complex interactions between multiple stressors, like how do warming and acidification together affect marine life? It's often more than just the sum of the parts.
Synergistic effects.
Exactly. We also need to better understand nonlinear responses, meaning changes might not happen gradually. They could hit sudden tipping points.
Right.
The specific vulnerability of commercially important fish species to acidification is another critical area needing more research.
Right.
And how different types of carbonate structures, not just corals but shells, seabeds, will respond to increasing acidity. The intricate links between acidification, upwelling changes, and oxygen decline, the socioeconomic ramifications of all this, how shifts in primary productivity will cascade up food webs, really understanding the cumulative impacts. It's a huge research agenda.
So while we've learned a massive amount, there's still so much more to uncover about this incredibly complex, vital system. Well, that was a truly deep dive into an immense amount of information. Let's come back up for air. What are the absolute key takeaways that you, our listeners, should really hold on to from all this?
I think the fundamental message is just crystal clear. The ocean is undergoing Significant, often rapid changes. And these are a direct result of human activities. These aren't abstract scientific findings happening out there. They have profound, far-reaching consequences for marine ecosystems, yes, but also for all human societies that depend on healthy oceans, which are basically all of us.
Right. And as we've explored, even seemingly small shifts, a degree of warming here, a small change in pH there, can trigger really significant, sometimes unexpected impacts. It just highlights how interconnected the whole ocean system truly is. Like you said, a giant, complex web tug one strand, and the whole thing vibrates.
Exactly that. And while our scientific understanding is constantly growing, constantly evolving, it's also crucial to remember there are still important areas where the knowledge is developing. Acknowledging those uncertainties is really vital as we think about the future of our oceans and the actions we need to take.
Which brings us perfectly to our final thought for you to consider. Given the sheer scale, the complexity of these changes that are now clearly underway in our oceans, what do you believe is the single most crucial action that needs to be taken to safeguard its future? And maybe just as importantly, what role, however big or small it might seem, can individuals like you play in that absolutely vital effort? Give it some thought, and please join us next time for another deep dive.